So I thought I'd do a video now, sort of revising my opinion to some extent on string theory. I don't think that my opinion about string theory as a theory of quantum gravity has ever much changed, in spite of a few things that I've read over, in string theory kind of lecture notes and things, and explanations of string theory, and research papers on string theory, and this sort of stuff, and Wikipedia entries also, a little bit sneaky, naughty. But yeah, I don't think it is the theory of quantum gravity, and I think the way that it goes about trying to be a theory of quantum gravity is kind of it's a bit like shoehorning. You know what I mean? It seems inelegant to me, in my opinion. Or it might be about quantum gravity to some extent. However, the realms in which it's dealing with gravity as a phenomenon are realms in which really gravity is somewhat beside the point, if you know what I mean. It's kind of expected for whatever reason. I'm not entirely sure why this is. I never really have been. Well, in regions like the singularities of black holes, like a quantum theory of gravity ought to be able to describe those regions of space, or those phenomena in nature. So I've never really seen string theory as the theory of that. In those regions, I'm just like, there's a lot of matter compacted into a very small area. There's a huge amount of density there. There's a huge energy density in black hole singularities, an infinite energy density, possibly. Oh, excuse me. The implication of that is obviously that at a very fundamental level, there's an infinitesimal of space, if there is to be an infinity of density at all. Whether or not particles are made out of strings, I don't really see why this explains anything much to do with black hole singularities, even. And more to the point, I don't think gravity as such, or gravity in the way that we usually think about it, is all that relevant in those areas of space. More like you've got this huge agglomeration of particles, I suppose quarks and gluons and things like this, and electrons, and this kind of balance of charged particles, really the electrostatic forces and the strong and weak nuclear forces in those regimes are more impactful or more significant. So yeah, I don't. But then again, string theory also purports to be a theory of everything. It purports to be two things, doesn't it? It purports to be a theory of quantum gravity, and it purports to be a theory of everything. However, what it isn't is a grand unification theory. So it does two things. It seeks to solve the problem of quantum gravity, and I think the sort of unanimous verdict that's dropped out of this in the mainstream of physics is that it has not been successful. It hasn't yet been a successful theory of quantum gravity. It's thought that in terms of string theories and superstring theories and these sorts of things, and now there's M theory, which is considered like a sort of a master theory, if you like, of all possible string theories. And you get numbers like 10 to the 500 different types of string theory, describing 10 to the 500 different types of universe with different fundamental constants of nature and things of that nature, things like that. And it's not yet considered a quantum theory of gravity, and I don't think it is one either. I read somewhere, I think it might be in David Tong's, is it Tong or Tang? I don't know. I think that's his name. A Cambridge theoretical physicist who wrote a series of lecture notes on string theory, and he was saying that string theory considers the gravitational field to be formed of quanta of the electrical field or the electromagnetic field, but it still talks about gravitons. If it's like quanta of the electrical field, then surely you're saying it's an electron, no? That's in the gravitational field, creating the force of gravity. And from that, then you can start doing a diagram of it. we've been doing for years and years with magnetic fields, as pedagogical aids and aids to our understanding of so we don't have to use just things like surface integrals and things like a very complex maths or rather intimidating maths to describe magnetic fields, though we do end up describing it with that also eventually. So then you can create a diagram of a magnetic gravitational field, which just looks like a cloud of electrons. The density of the composition of the cloud of electrons diminishes in inverse proportion to the square of the distance, just like in Newton's laws. But instead, we don't have that, and we still teach people this kind of trampoline model of gravity from Einstein, this space-time stuff, this stretchy, squeezy space-time from general relativity, and put balls on trampolines and things to try and describe it. So it's confusing. It seems unclear. Its theoretical applicability in the study of gravity seems to me to be off. It seems to me to be limited. However, I wouldn't have said therefore that there aren't rather profound and very serious insights to be had within string theory into nature. I'm not there's all this new stuff from there's ER equals EPR stuff. I can't remember his name. Jesus Christ. Juan Maldacena. Yeah, this sort of one of the new great physicists, or one of the sort of physicists who's touted as being the next Einstein or something like this. To ER equals EPR stuff. The Einstein-Rosen bridge is macroscopically equivalent to a superposed set of Einstein-Podolsky-Rosen connections, entanglements. No, convolutional entanglements. Great. No, sorry. Yeah, EPR paradox. No. Einstein-Rosen bridges are equivalent to a superposed agglomerated set of Einstein-Podolsky-Rosen paradoxes, i.e. quantumly entangled particles. I don't know, in the face of what other elements of physics ought to make things like the instantaneous transmission of communication or wormholes impossible. It's Bell's theorem and Bell's inequalities and this sort of stuff. But yeah, yes, I don't know. Does information go in one way but it gets scrambled, maybe? And maybe can transport things instantaneously, but the universe will fuck with it somehow and prevent you from making it work. Or test you to see how clever you are. Unpicking the or trying to hack it. That's what you're trying to do. You're trying to hack the universe, aren't you? We would if we could. Oh, we would. Yes, we would. Yeah, we would, definitely. Who doesn't want to get to somewhere else in the universe instantaneously? But then again, that's again to facilitate ease of travel within the universe. So we travel places instantaneously. But I mean, why do we want to do that if we could just travel at the speed of light and not experience the journey? We seem to arrive instantaneously anyway. It makes a difference. But I mean, nonetheless, I don't believe in string theory. Still, I don't. I believe in my theory. What I've tried to figure out, which is the gravito-electro-weak interaction. So how the electro-weak interaction gives rise to gravity. So the model I propose is sort of at the macroscopic level, a gravitational field formed of a cloud of electrons. See the logo of my channel. That's basically what I'm proposing. Obviously, there'd be way more electrons than that. I couldn't possibly ever like put them all in a diagram. It wouldn't be reasonable. It'd be like 10 to the 53 electrons per second. Some astoundingly huge number, but yeah, nonetheless a finitude over a given amount of time, over a discrete amount of time, there would be some finite amount of electrons. But and then these electrons tunnel to within the first electron shell, or inside of the first electron shell of, like, say, a hydrogen atom. So an electron from another object will tunnel into this bit inside the outer circle, and it will exchange doubly plus and or minus particles. Or no, it'll exchange a doubly minus for a doubly plus from the proton within, say, a hydrogen atom. And in doing so, the hydrogen atom will be drawn in macroscopic space slightly closer to the object from which that tunneling electron had originated. See what I mean? Or in that direction, you know. And this is what causes large-scale objects in the universe to be attracted to one another by gravity. And it also has the effect of slowing objects down, or ensuring that the way that they travel through space isn't infinitely quick. So what the string theory really is a cop-out. What it is it just invokes new particles. Oh well, it's a spin 2 massless particle called a graviton. We haven't found it. Like, now we'll find. Maybe find it. Like, maybe it's like, I don't know, some high energy that we can't detect yet. Like, okay, cool. Like, you're multiplying entities beyond necessity. That's why you're wrong, I think. Like, it might, like, strictly be science, you know, in theory. If we build a huge particle accelerator around a neutron star one day, or around the entire galaxy, maybe we could achieve those energy levels. But it's a cop-out, because we won't be able to do that for thousands and thousands of years. But it passes empiricism. It fits just in the scientific method. It does. Like, in theory, it's testable. It's hence a hypothesis. There is no evidence from experiment at all supporting it, however. And it fails the test of rationality, because it multiplies entities beyond necessity. So I do not believe in string theory.